Good morning, everyone, and thank you very much for inviting me to Surgeon and for inviting me to this very nice course. Okay. I am essentially a robotics guy. I am part of a robotics group, okay, at the University of Seville in Spain. And what I'm going to speak about is the cooperation about unmanned aerial systems and wireless sensor networks for advanced monitoring systems. This is the talk number 3 from Planet Project. And in our group, we have developed, we have been working in unmanned aerial systems for the last, let's say, 15 years approximately. During this period, we have developed a number of monitoring systems. We are very committed to environmental protection. So one of the applications that we have researching quite intensively has been forest fire detection, monitoring and measuring, which is a problem in Spain. So we have developed a number of systems in which aerial systems cooperate between each other and also cooperate with the static systems in order to have in real-time forest fire detection, monitoring, and also measuring. To have information in real time about the fire status is very important in order to plan the attack and to efficiently being able to fight the fire. So at the beginning we started approaching the problem using only static stations, cooperation between different static stations. Then we put some mobility, first manned helicopters, like those that are currently being used in forest fire protection. Then we use robotic helicopters. And finally, we are proposing, we have done a number of projects with the cooperation between flying robots and static stations. This is essentially one of our flying robots that they use in these experiments. Essentially, it's just a number of sensors, GPS, it's also communications, and also a number of sensors that are basically an infrared camera and a visual camera. And here there's an electronic box in which there is a number of algorithms, both for perception and also for navigation of the helicopter, are being implemented and running during the fire. Okay? We tested this system in real fires. This is one example. This guy running with me. Believe me that the temperature about 30 meters from the fire was really hot. Okay? And this is one of the pictures of the experiment sites in which we have developed a number of experiments for more than 10 years. We have burned about 10 hectares, 15 hectares each year. Okay? And the objective was to model the fire advance. It was a multidisciplinary project. We were responsible of giving real-time measurements on the forest fires, and these measurements were used by other biologists and by other forestry engineers in order to model the fire advance. Okay? This was our role in this. And of course, this is some of the results. Here we have the results, the measurements we've got from the aerial systems. In this case, each of these lines is a geo-referenced location of the fire of the forest fire front and each time. Okay. This is also what we've got from the infrared camera. This is what we've got from the frontal camera. And of course, one of the main topics here is to fuse this information. Forest fires and in general environmental systems are very full of noise. There is a lot of uncertainties, noise that pollute the measurements. So we have to develop a number of techniques in order to fuse, combine this information, let's say in an optimal or let's say in the best possible way. Okay? This of course was the main topic of our research. And this is some of the results that we've got. This is another experiment, also the visual camera and infrared camera. This is some of the results number 10. And in this case, this is the most advanced point in the fire. Okay. This is the time and this is the meters. And we validated that with real field measurements. Can any one of you imagine how these forestry guys measure the advance of the fire? Can you imagine?
Temperature.
Sorry?
Temperature maybe?
But how? How? You mean you deploy a number of sensors and you do what?
Yes. You try to detect where temperature changes very fast.
These guys are forestry engineers. Okay, there's there's not too much technology, too much networks in order to in real time measure the temperature, to log all that, you know. And this is real forest. I mean, this is the this is in the middle of nothing. You can imagine in the middle of the field. There's no electricity. There's
so it's smoke.
It's smoke. No, yeah, but the exact location of the fire in real time. Sorry?
Satellite imaging?
Satellite do not provide enough resolution in order to have the accuracy they want. Okay.
Maybe cameras and thermal vision somehow.
That is our role. Okay. Yeah. So before, what they did is to measure that, just deploying a number of threads. Okay. A thread. Okay. With a small bell. So when there was, when the fire cut the thread, a small bell, ting, 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 and one guy listening there and chronometering the sun distance. That way, exactly that way. Okay. So these are the measurements that they got. Okay. 0. These are the times in which the cuts were the threads were cut.
Just
okay.
one small question. So, which kind of birds exactly? Because if an animal is passed by, passed by a thread or something like that.
No. It was just the fire cutting the thread. It was a thread, and it burned and it broke, and then the bed. Then the guy being there.
Something else, animal, something, or yes.
No, because in this experiment there were a lot of people. In this experiment about 300 people were involved, so animals left before. Okay, about 300 people, so about 200 firemen. Okay, about 100 researchers, more or less, for different sites. Okay, different. This was a huge experiment we've been involved. Okay, this is not the topic that I want to show in this presentation, but this is just to focus our expertise in this problem, in this. Okay, because it's not always to have let's say a technological flavor of the problem. You have to be inside. You have to suffer. You have to have real contact with the thing in order to do things. Of course, in these times we develop a number of patents and publications. Here are a few of them. Okay. And of course, we are very committed with environmental problems, environmental monitoring problems, and in this case, in this forest fire, we offered a number of solutions, okay? But we are interested in, let's say, more advanced topics. Let's say, for instance, there are many environmental protection problems in which you need a combination of both large-scale measurements together with very local measurements. Okay? Imagine, for instance, that you are in a pollution event and you want to know the coverage, the real estate of the pollution, at large scale, okay, several kilometers. Okay? And also you want to know the exact concentration of pollutants on a certain location. This cannot be done using only UAVs. Okay, this should need another of cell technology. So we started using water sensor networks in forest fires. We deployed a number of nodes there. We measured the temperature until they died. They were burned, of course. Okay, and our idea in Planet was to combine this kind of technology. Okay. Of course, we all know about water sensor network technology. One node by itself is a crappy device. It's low cost, it fails a lot, communication range is nothing, lots of uncertainties in the measurements, low memory, low computing. The strength of the water sensor network comes from the network, okay? From the capability of interchanging measurements and interchanging data and fusing data. This is the strength, okay? On the other hand, we have unmanned aerial systems. For us, it is essentially a flying robot In our group, we are about 60 researchers that are mainly dedicated to aerial systems, okay? About 10 professors, more or less. About 12, 15 PhD students. I have 5 PhD students under my supervision. And here for us, for me, for let's say our part of the group, okay? My part of the group is a tool that is endowed with a number of functionalities, such as control, navigation, perception capabilities, and also they can carry devices, they can deploy devices. Okay. Of course, we can have different platforms, we can have fixed-wing UAVs, okay. They have a number of properties, a number of disadvantages, it depends on the application. And we also have rotary wings, essentially we have the helicopters, and we also have quad rotors. Quad rotors are more suitable for indoors applications. They have low autonomy and they have very low payload capability. Helicopters are more suitable for outdoors application because, let's say, it is quite dangerous. I've been to several accidents in here. It's impossible to find if you know one guy that says, "Oh, I have UAVs," and they didn't have no accident at all. He's lying. He's lying. He had accidents, or he's not working in UAVs. Okay, but it's impossible. Okay, or he just started 2 months ago, and he still hasn't fly. Okay, hasn't flown. So, what we are trying to do here in Planet Project is to exploit the complementarities between wireless sensor networks and humanitarian systems. Of course, if we take into account their capabilities, aerial systems have actuation capabilities, wireless systems have very low actuation capabilities. The variety of sensors I can put in on aerial systems is quite large. Okay, it depends on its payload capability. While sensors, in case of sensor networks, let's say that the sensing capability is quite constrained, at least in comparison with aerial systems. The energy consumption constraints are harder, are stronger in sensor networks. Also, the communication range and communication bandwidth have more limitations. But of course, these are some differences. But of course, it is very interesting for us that the wireless sensor can be used to obtain very local measurements, while aerial systems can take largest measurements. That is very interesting for us. And another possibility that we have is that one aerial system can deploy sensor networks. So it's very easy to devise strategies in which an aerial system deploy a number of sensors, interchange information with the sensor nodes, okay, integrate this information in order to have a more accurate monitoring of the event. So this is essentially what we are exploiting in the Planet project and our role in the Planet project. I will shortly go into some details. Then I will go into one experiment, one application within Planet, okay, in which I'm going to describe some of the strategies, of the cooperation strategies that between wireless sensor network and aerial systems. Okay? Particularly, I will describe cooperative surveillance between aerial systems and wireless sensor network, deployment of wireless sensor network using aerial systems, the, data collection, and also pollution sampling. So this is the basic scheme of the Planet project. Yesterday you learned about this. Essentially, there are a number of stages, and there is a closed loop approach. That means that you plan a certain deployment, you deploy, you measure, you assess the quality of the deployment, and then you reconfigure that in a dynamical way. Okay? From that point of view, it's very interesting to have actuation capability, okay, robots. In Planet project, ground robots and also aerial robots are involved. We are responsible of the aerial robots. So this is the planet's architecture. Essentially, you have a number of modules. You have a user here, a user interface, a visualizer, planner, simulator, control, which keeps the information, the main intelligence of the planet system. You have communication modules here, platform, and also you have the devices. You have, in devices, you have the sensors, you have the aerial systems, and you have the ground routes, essentially. Okay, we are going to test this development in one scenario, that is the Doñana National Park. It is one of the most important, largest environmental sites in Europe. It is located at the south part of Spain. And one thing that is very interesting is that it's very dynamical. There are areas in which there are marshes. Okay? So during the winter there's water. During summer it is dry. So there are a lot of changes, and the system should adapt to these changes in a dynamic way. That is a challenge for the planet project, of course. And in particular, I'm going quite to the point in this part. In particular, we are going to address one of the applications, which is the monitoring pollution application. Imagine, for instance, that we have a pollution event. In the surroundings of the natural park, there are a number of factories, there are a number of mines, okay, that could produce pollution. In fact, we had an episode about 15 years ago that was a dramatic episode. Boliden Apirsa, a huge company, split thousands of tons of waste from a mine, and it caused a really damage. Okay, heavy metals, etc. Lead. Okay, so the idea here is to develop a number of functionalities in order to protect the park in case that we have a pollution event. Of course, this is a project. This is not to be applied. Okay, this is just to be demonstrated in this scenario, but it could be applied, of course, if enough resources are put into that, of course.
Sorry.
Yes.
Yes. Question. Also, yesterday someone told us about this project. So on one side you have the monitoring of these pollution events, but are there any ideas about what to do in case you recognize this event?
Well, in this case, of course, there is an operational point of view of the problem that is out of the Planet project. The objective of Planet is to provide tools in order to help to this operational side. Okay, this is out of the project. This is much depends on civil production, on
maybe the biologists or the people with
civil production, etc. Of course, what they need and they don't have right now is real-time measurements. They are very important for them. In this scenario, you can imagine there are marshes, so it has a very difficult accessibility. It's not easy to say I want to measure what's going on here, what's going on here, what's going on. That is very difficult and very costly. You have to go by boat, essentially. By boat or by horses, I don't know, okay? This is very difficult. So it's a challenge to have measurements in this case. And also in the case of the forest fire, it is something similar. It is very important to have in real time the status of the event that you want to fight against, because otherwise you don't know what are you fighting against. Okay, so the part here is to have real time information about what's going on. How to fight is out of the project, okay? So, of course, we have a number of challenges from a technological point of view, what we are interested in, essentially, which is the integration and cooperation between aerial systems and wireless sensor networks, okay? And in particular, the deployment of wireless sensor networks using aerial systems, the repairing of wireless sensor network using aerial systems, the cooperation between aerial systems and wireless sensor network in order to track different nodes that can be in animals. You saw yesterday a number of things also. And also the processing and forwarding of complex data. You can imagine that modeling an event, a pollution event, is quite complex in terms that it needs complex data, complex models. Okay, so this is also a challenge for this project. In our case, this talk is going to focus on a number of strategies in order to cope with the pollution monitoring problem that I said before. So imagine that you have a big company such as Bolivena Pizza, which splits tons and tons and tons of waste of heavy metals there. So what can we do there? Well, there are a number of problems. The first thing is to have a general overview, a general status of what's going on. Okay? So for doing that, we need devices that can have large coverage. One option is satellite. Okay? The problem of the satellite is that the satellite that can, let's say that satellites are not suitable because they don't provide enough time spatial resolution. There are high orbit satellites that are able to provide very high temporal resolution but very low spatial resolution, and there are low orbit satellites that provide high spatial resolution but they pass over the same area every 3 or 4 days. So this is not enough for this low temporal resolution. So the solution that we used was to use aerial means, of course, and to do it in a robotic way, in an autonomous way, using a number of UAVs. So a number of UAVs cooperate between each other in order to survey the area, okay, in order to have some kind of global estimation of the status of the event. Okay. Once that we have that, we have a global overview. We would like to know what is going on at a certain number of locations that are more of interest because of biological reasons or whatever reasons. So, in this case, we need local measurements. What can we do? What we can do is to deploy sensors there. Okay, which sensors? Well, it depends on the technology we are using, but of course, these sensors should take measurements and communicate the measurements out of the system. So, in this, we are using wireless sensor network nodes, of course, and who is going to deploy the sensors? As I said before, there is very low accessibility, so the best option is to use UAVs. So UAVs are commanded to fly to deploy a number of sensor nodes with the specific sensors for the application at a certain location. Okay, now we have sensors there, but we need to get the data. And we know that the communication range is constrained because of the battery, the energy, etc. So, what can we use? One alternative is to deploy thousands of sensors in order to have a multi-hub network to a certain base station. Another option is to use aerial systems in order to communicate with the sensor nodes, establishing a certain protocol, and the sensor nodes transmit the data back to the UAV, and the UAV, which is not as constrained from the energy point of view as the sensor nodes, transmit the measurements outside to the base station. Okay? This is the data collection with UAVs. Okay? And finally, in some cases, it is interesting to take physical samplings because in some cases there are not suitable sensors to measure a certain type of pollution, a certain type of metric that they want to obtain. So the idea here is to obtain a certain sampling. By how? As I said, there is low accessibility, so the best option is that the robot go there, deploy a small robot, the small robot just picks a sample, okay? The small ground robot is taken by the unmanned air vehicle, okay? And then it's taken somewhere. Okay? So these are the examples I'm going to show. These are applications that are going to be demonstrated in 2 weeks' time, okay? Because we have one experiment in Doñana in 2 weeks' time, and all of these are going to be demonstrated. Hopefully, let's see what happens. And this is the main topic of my presentation. These are some credits. These are some of the PhD students that are working with me in this, okay? Alberto Sanbernabe, which is working in localization and tracking. He's going to finish his PhD this year, sure, this year, next year, this course, I mean. Karim Elfer, he's working in data collection using aerial systems. Santos Castañé, he has developed the small deployable node, a number, and also Arturo Torres, Gabriel Núñez, okay? This is the web page of my group, the group I work with, and this is the Planet website, okay? So, I'm going to describe one by one each of the applications that I said before. One I will describe more deeply, one not so deeply. I'm going to describe this as let's say, an overall description, because I think it falls out of the topic of the course. It is more related with a robotics course. So in this case, we want a number of aerial systems to cooperate between each other in order to survey an area. Of course, we are assuming the area is very large. We're speaking about thousands of hectares. So we cannot assume that the aerial systems can communicate with each other. So essentially, we have a number of aerial systems that are out of the radio coverage one each other, okay? And they have to cooperate in order to have a survey of the system. Okay, also one important constraint is that it has to be able to dynamically adapt to the changes, and also there are a number of static sensors, and if there is a static sensor already deployed, it makes no sense that the UAV goes and measures more, because it has already been measured. Okay, so we develop an algorithm which is based, it's a decentralized scheme. Okay. And essentially, the centralized allocates the UAV to certain areas in a dynamic way. Okay. It is decentralized for both reasons. First, because the area systems cannot speak with each other. Okay. First reason. The second reason is for robustness. Okay. In this case, this is, let's say, a topic typical in the robotics domain, and I'm not going to go too much detail into this, okay? But we have developed a number of novelties, a number of publications that I'm not going to describe. But essentially, the main topic is that the coordination between the different UAVs is done by means of something which in robotics is called coordination variable, which is a minimum number of variables that allow the system to coordinate. And just, I'm going to put an example. Imagine, for instance, that we have, this is the area that we wanted to survey. The stars are static sensors. These things are, the arrows are UAVs, and the arrow means the direction of the movement. So in this case, consider that you have a number of UAVs. The number can be whatever. There's not a constraint in that number, because the method can adapt to the available means. And in this case, the initial state is like that. It can be whatever. Okay. After a number of iterations, okay, the algorithm is capable of identifying which areas are already covered by static nodes. Okay, and the area that is uncovered, okay, is distributed among them. This distribution is not static, it's only dynamic. In this case, we have 5 UAVs, so this is the distribution. But in case we have 4, distribution would be another one. Okay, this is dynamic. So imagine, for instance, that now 2 alarms have been detected, 2 points that have been identified. They require special monitoring. Imagine, for instance, in case of a city, there's a city here, so the pollution is reaching to a city. This is very dangerous. They can be dangerous for the water, etc. So they want to monitor with high accuracy what is going on here. Accuracy means also temporal accuracy. If you have more aerial systems in this area, so you can have measures more frequently, which is good for the monitoring. So in this case, we deployed a number of alarms. One alarm is already covered by one static sensor, so the algorithm is modified in terms that it gets more measurements from the alarm. But in this case, what is done is that the UAVs reorganize each other They reorganize each other in order to have more intense monitoring in the areas that are more interesting. Okay? So this is the result of the algorithm. We have tested that in a testbed that we have and show later, and a testbed with ground vehicles, and also a testbed with flying robots. Okay? But as I said, I wouldn't like to go into much detail this because this falls mainly in the robotic part, and maybe it's not of interest for you. Okay. Okay. So once that you have identified a number, once that you have identified the global area, then you want to have local measurements. How can you do that? Deploying nodes. So in this video, I'm showing a result of a previous project that we coordinated. It was a FP7 project, okay? And it was the iWare project, that is the web page. In this case, we applied this kind of cooperation between wireless and airlines to forest fire, to industrial fire protection. So in this case, here is a fire, okay? And also the helicopters with a camera can identify a number of threats because there are a number of barrels over there. So the system automatically identifies the threat that the fire burns the barrels and destroy. Okay, the barrels can potentially be with some explosive or some gasoline, etc. So the idea is to monitor, to intensify the monitoring in the areas between the fire and the threat. Okay. For that, a number of nodes are deployed. The helicopter, in this case, 3 nodes are deployed. So a number of positions are identified. The nodes are deployed. Once they are deployed, they connect to the wireless system that is already deployed in the system, and they provide measurements of exactly what's going on at that location. This is something, as I said, that I tested in a previous project, a work project, and in this case it was coordinated by Sevilla, by us. Right? This is the second node. We developed some kind of node parachute. Of course, the idea was only to reduce a little bit the speed in order to prevent break. It's not a parachute itself, okay? Because we also wanted to have accuracy in the deployment. So if we decide to deploy at this location to be there, you have a parachute, then there's wind. So in this case, we got an accuracy of 1 meter something like that, which is not bad. This is one experiment that we tested in Sevilla. Okay? Okay, the deployment of wireless sonar can be done by 2 main reasons, I think. The first one is to intensify monitoring, to exploit the sensing capabilities of the nodes. Okay? The second is to exploit the communication capabilities of the nodes. Okay? So one typical application of wireless and sonar agnostic operation with aerial systems is to repair a wireless sonar. We also have developed a number of systems, of techniques, and a number of publications that work with that. In this case, we assume that there are a number of static nodes that are deployed at certain locations, and the objective is to obtain a diagnosis of the network, identify holes, identify clusters if it is disconnected, and then to perform 2 stages. The first stage is to repair the connectivity, essentially to deploy nodes in order that the whole network has a certain level of N connectivity. N connectivity is a metric, it's well known, I think. Okay, so to ensure a certain level of N connectivity, but there is another step, which is to ensure redundancy. There is also one metric that is called N redundancy. Okay? So in this case, we deploy nodes first to recover connectivity, and then to recover a certain level of redundancy. This is one example of one experiment that we performed in a previous project, also European FP7 project. In this case, is the Connect project. In this case, here is a number of nodes that are already connected. During the diagnosis stage, a number of robots just survey the environment, identify the nodes, more or less located the nodes using signal strength, okay, and also identify the topology. Once that we have the topology, then it identifies that it is disconnected and identifies the location where the optimal location where the deployment of one node could recover connectivity. In this case, if we deploy one node here, it has one connectivity that can be enough. Okay, this is the objective of the steps to solve the connectivity. And then the next step is to solve redundancy. So we use the concept of N redundancy in order to identify nodes that have very low redundancy. In this case, for instance, if we delete this node, or if this node fails, then the connectivity will be broken. So this node has N redundancy of value 0. Okay, this has of value 1. This also has of value 0. If it's deleted, it is disconnected. There's a number of papers dealing with that. I will not go in much detail. Okay, but you can ask me now or later or whatever you want. Okay, but in this case, the algorithm decided that the best choice to improve the redundancy of the system is to deploy 3 nodes. One node to deploy here. In this case, this goes to a redundancy 1. This goes to redundancy 1. And one node here, redundancy 1. Okay. And another node here. In this case, it goes to redundancy 2. This means that all the nodes have N redundancy 2, that according to the publications, it is considered robust. We performed this in an experiment, as I said before. I think the video should be here, okay. This is one experiment that we performed there in Seville. This experiment was demonstrated in real time online during the review of the project. It was nice. The pressure, but it worked, okay. So the idea, here are the nodes. In this case, they are deployed on these small platforms. Here are the robots, okay. So in this stage, they are just surveying in order to obtain the topology and the location of the nodes. In the next step, once they have the location of topology, you perform the rest of the steps. Okay. One video, I think this video, you can see that in this, which is a web page of a system that is related to the project I'm going to describe now. This experiment was carried out in one infrastructure that we have in Seville that I would like to let you know, to disseminate here, which is the Connect integrated testbed. Okay, this is a testbed that is fully open, and in this case we have the cooperation between static nodes, okay, and robots. Each of the robots, well, we have a static infrastructure with a number of nodes. We have Telos B, Nika 2, Nika Z. We have also these two. We have 5 different nodes, about 200 different nodes, okay? And also we have a number of robots. So each of the robots, which is this and this, have one node, okay? Apart from the sensors, from the robotic point of view, laser, camera, etc., okay? It also has one node. It means, and also that node is physically connected to the robot. There is a bidirectional protocol by means of which they can speak. They can interchange commands, requests, data, in such a way that one robot can command a node to take a measurement of temperature or whatever, okay? And the node can command the robot. The node can command, please go there, because I want to join my friends or something. I want to join the rest of the nodes that are there, okay? So it is, I think it's quite interesting, okay? It is open. It was developed in the project Cornet. It is an award of excellence. We were involved, deeply involved. We were associate coordinators of this. Okay, this is the architecture of the Cornet of the let's see of the testbed. We are using as basic framework one middleware, which is called Player. I don't know if you have heard about that. Maybe you have heard about ROS, Robotic Operating System. Okay, Player is the predecessor of ROS. It was also developed by Brian Gerke, which is the main developer of ROS. Okay, okay. So let's say that ROS is an evolution of Player. When we started with this, 6 or 7 years ago, ROS simply didn't exist. Okay, so we choose Player in this case, and Player makes transparent communication between programs and devices, essentially, in a networked environment. So these are the processors that are running in each of the computers. There is a server that is responsible for communicating with the hardware, okay, and there is a client that you can just put into your program, the user program, and the user program just use a simple abstract interface in order to communicate with the hardware. Okay. Also, from each of the clients, you can communicate not only with your server, but with the server of any of the robots. Okay, and also it is based on TCP, so you can just put it in the internet. And you can develop a remote station in the internet. Okay, you can just connect to the internet. So it's a remote testbed. It's open, and it would be nice if you decide to perform experiments there. Okay? This is the infrastructure. This is the deployment of the infrastructure. Essentially, we have a tree-like USB in order to connect all the nodes. These are each robot is equipped with a Kinect sensor, with a laser, and with a node, and also 2 processors, one of the robot itself and one for the high-level software, high-level programs. And this is a skin of the protocol between the wireless sensor node and the robot. The protocol has been the protocol has been developed in 2 modules. One module that is within Player, another module that is within TinyOS. Okay, it also works with Contiki. We also tested that with Contiki, and the module of Player is already now in the distribution of Player. So we got it accepted within Player. If you download Player, it is already with that module. Okay, this is some hardware description. Okay, you can have the platforms, the different features of the sensors. Okay. From the user point of view, there is a page in which you have to register in order to use the testbed, which is connect.us Universidad de Sevilla.es, Spain. And then when you register, you can have access to a number of documentation in order to use it. You can just install, because there is a virtual machine that you just download, and everything is there, so you can. And also the communication is through the internet using the VPN, so it's private. It's nice. Okay. Also, there is you have to speak with an engineer who is responsible of the experiment. Okay, because the experiments are attended. If you are using the robots, the experiment should be attended in case something happens, a crash of the robot, something. Okay. But if you want to perform experiments using only the nodes, so it's possible to do it unattended. In this case also, the experiment, the infrastructure has a number of basic functionalities in order to control the robot. Okay, so you can just use that functionality and you can have full control of the robot. You can say, this robot go there, you can upload code to the robot, to each of the nodes, to each of the robots, all together. You can log all the data, download the log. You can imagine all the functionalities typical of a test. This is also, we have a graphical user interface, which is very easy in order to monitor the experiment in real time and to see what's going on, in order to upload the code. Okay. And a number of cameras that you can connect to, and you can see the experiment by yourself, even you are several 100 kilometers from there. And okay, a number of publications have been there. Next month there will be one book in Springer regarding this. Okay, if you want to take a look, here it is. Okay, we keep on with the with the main trend, the main theme of the topic of the presentation, and we go to another application. Once you have the node deployed, you want to take the data from the node outside. How can you do that? The way that we are proposing is to use UAVs. Okay? Ground robots are very difficult to use because there's bad accessibility there, as I said. There are marshes, water, there are, this is a park, okay? But the UAV is much simpler. And also, the UAV has the possibility that the communication is simpler in terms that ground-air communication is more efficient, so it reaches longer, it uses less energy, so it is quite suitable. Of course, we can decide to use fixed UAVs or rotary wing UAVs. The rotary wing UAVs, helicopters essentially, and quadruples have higher maneuverability, okay, which is good indoors. But if you want to have several kilometers, and you need a device that spends very low energy, and this is got with planes, with fixed wing UAV. It's more efficient in the use of the energy. Okay? So in this case, we use fixed wing UAVs. Okay, of course, we have to develop a strategy in order to perform the collection. Okay, the baseline scheme, which is most of the publications have. I think all the publications regarding this have worked about, is to have a baseline scheme in which the UAV just send a protocol to the establish a protocol with the nodes with each of the nodes. So the UAV just visited the node, transmitted the message, and the node transmitted back the message with the data, and it forwards to the base station. This is the basics. But this is not scalable, and we are a problem which is scalability is very important. So our approach is different. Our approach is based on clustering. Okay. So essentially, we have a cluster of nodes. Okay. The nodes that are deployed organize themselves in a cluster. There's one head, and the cluster head is responsible for communicating with the UAV. The rest only communicate with the cluster head. So it is more efficient from an energy point of view, scalability point of view, etc. Yes.
How do the sensors communicate between themselves and the cluster? What protocol do they use?
They use. We are using TDMA. Okay. So I'm going to describe it a little bit later. Okay? Also, it is very interesting for us because we are very interested in artificial intelligence. There is something that is called emerging behaviors. Okay? So in here, what we are looking for is to have some kind of impact between wireless sensor network and UAV. In fact, in the system that we develop, there is an impact because when you change the cluster head, because the cluster head spends more energy than the rest of the nodes, so you have to change it from time to time. So when you change the cluster head, so the UAV should take another trajectory, because otherwise maybe the connection is not good. So that means that the performance of the wireless sensor affects the UAV. Okay. But on the other way, the UAV trajectory is also should be taken by the performance of the wireless sensor network. Why? Because what we would like to have is to modify the trajectory of the plane as minimum as possible. That means that in the selection of the next cluster head, we want that the UAV keeps the same trajectory. We want to modify as less as possible the trajectory of the UAV. Why? I'm going to go into more details about that. Okay. But then in the rotation, we have two terms. One term that is related with the energy. We select the node that has more energy. Okay. Another term that is this node is more suitable because it implies less motion in the trajectory of the UAV. Okay. So there's a coupling here which is interesting for us. This is essentially the scheme. We have a number of steps. The first step is the network partition, which is a protocol similar to Leech. Okay, so there are a number of candidates that propose themselves using a metric. they just select one candidate, another candidate, and they subscribe to, okay, they decide to be with that candidate, and this is similar to this, essentially, okay? Once that you have that, the cluster head establishes a TDMA scheme and broadcasts that, and of course, there is two streams of communication. One is on ground to here, okay, and one to the helicopter. So this spends significant energy, so it should be rotated. And in the rotation, as I said, each of the nodes that are candidate to be the next cluster head are evaluated using both energy and also a term that depends on the minimum deviation of the UAV. So this is the minimum deviation of the UAV, okay, and it weights with a different weight in order to have adequacy. At the end, the node with the highest adequacy is chosen to be the next cluster. Okay. Of course, this is the strategy, but from the UAV point of view, we also need some kind of a strategy. So we also need to decide which is the best way in order to collect the data. We need to allocate the clusters to the UAV. We have to decide which are the path, which should be the path of the UAV in order to collect all the data with a minimum time. Okay? For doing that, we develop an algorithm which essentially solves the problem, solves the tradesman, the travel salesman problem, okay? But it is not exactly like that. It's a little more complex, but essentially it is like that. First, we solve that without considering the kinematics of the UAV, okay, in this step. And then, in the following step, we consider the kinematics of the UAV. The UAV cannot move like this, okay? It has a kinematic. So we have to consider that into the algorithm. So this is one example that we have a number of clusters. These are the cluster heads. Around each cluster head there is a weight zone. That means a zone that should be passed through the UAV. So in this case we apply the algorithm in order to allocate the nodes to the UAV to only one UAV, and this is the trajectory it provided, okay? And in case that we have two UAVs, because maybe in this experiment 2 or more UAVs are required to do that, and we have to consider scalability, and of course the algorithm considers that. In this case, these are the trajectories for UAV 1 and UAV 3. It is very interesting to consider the duration of the lap, because the duration of the lap essentially means the latency in gathering the data. Okay? So in this case, using only one UAV, it took about 2.4 kilometers. Okay? And using two different UAVs, the lap in this case took less than 1 kilometer and less than 1 kilometer. That means that using two UAVs, the sum of the length of the path of the two UAVs is lower than the size of the length in case you're using one. That is very interesting. Okay? Because in this case, scalability is positive. It's positive.
Excuse me, you use the term problem approach or nearest neighbor?
We use a problem. We use the first one. Yeah, but using several travelers.
Okay, so it can be considered there are a lot of heuristics that solve, for example, even vehicle routing problem or multiple routing problem.
Yeah, exactly.
I'm interested in this neighbor, nearest neighbor. Actually, I encounter a lot of problems if you want to use simple next nearest neighbor. So do you, essentially my question is do you do it in a centralized way prior to prior to
exactly.
Actually
Exactly.
You do the pipeline in the beginning.
Exactly.
So you need the exact position of each node.
Yeah.
And did you maybe
You have deployed that with an helicopter. You more or less have 1 meter accuracy the locations.
Did you maybe think about about some stepwise solutions.
Some?
Distributed stepwise solutions. So I visit one node and then I'm thinking where to go next.
In this case, we are focusing on a centralized solution. Yeah.
Okay.
And in a distributed, I think it could be very interesting. But in this case, we're using just one. Also, we use the salesman travel problem only for the initial part of the algorithm, without taking into account the kinematics of the UAV.
Of course, yeah.
Okay? And in order to assign the order of passing through the UAVs. Of course, then you have to refine that solution using the real kinematics, because there are some solutions that are not possible. You cannot do if you have this and this, you cannot do it like this. So there are some constraints that in the first step are not taken into account in order to simplify, in order to have a quick solution as fast as possible. Okay? And then we go to that. And of course, we don't implement the full salesman travel problem, which is NP hard, which is okay. We implement a heuristic based method that is based on nearest neighbor, as you said. Once that you have at one point, you identify which is the next one, and in the next one, then you try to focus that. Yeah. Exactly. That is the option that we do.
Thank you. I will ask you more questions.
I just have one question. Do you work in separate ways in this project and the one before, dealing with the network protocol? Because the sync, the local sync, will need to be changed to not dramatically decrease energy. So how do you know which one is the
Yeah.
Yes.
I mean,
this one.
How do you know which one is the cluster head?
Yes, cluster head.
Of course, I'm going to describe it later. Essentially, what you have an area in which you know that the nodes are deployed. Okay. Then with the helicopter you perform a thick-thumb pattern. You activate the node. Okay. Because they can be sleeping or okay. So you activate the node. Once that they are activated, they start the network formation. They decide. Sorry.
All of them, or just the?
All of them. All of them are sleeping.
All right.
All of them are sleeping. Okay. Then you activate the node. Then they are organized using this protocol, and some of them are decided to be cluster head. Okay. Then the UAV goes another thick-thumb pattern, asking who is leader, who is leader, who is leader. Say me node ID X, I'm leader. Me node Y, I'm leader. So he knows the location. Then he knows where he has to fly, and then it is the second more strategy path is done. Do you see what I mean? So at the beginning, all the nodes are exactly the same. Okay. So you activate the node, they are using a thick-thumb pattern, okay? And when you have the thick-thumb pattern, you activate the node, they organize themselves, they decide who is the cluster, who is the cluster leader, the cluster head of each of the cluster, but you don't, the UAV doesn't know them.
How do you transmit this information? Who is the leader to the helicopter man?
Yeah. In the second, yes, there is a step in which there is a thick-thumb pattern, okay? In which
how do you retrieve the information? How do you retrieve it?
Yes. Yes, there is a step in which there is a thick-thumb pattern, okay? And he is asking who is cluster head. The cluster head, only the cluster head responds. So the plane knows that node ID X, Y, and Z are cluster heads.
So it needs to move.
Of course, there are several states. I'll describe this later. There is a state machine in which there are several stages, several. So here's the result of a simulation of 16 different scenarios, randomly deployed nodes, okay? And they at the time required for data collection using one UAV, two UAVs, and three UAVs. And we see that the time is about 1 divided by the number of UAVs. So this figure is interesting to justify the use of several UAVs in this program. Of course, it depends on the methods, on the means that are available. Another important effect with UAVs is uncertainties. Okay, wind highly affects the flight of the UAVs because UAVs are lightweight. I'm speaking about 20 kilos maximum, 30 kilos maximum. So if there is some wind, so the controller not always is capable to compensate the wind, and in the end there is an error. This is one experiment that we performed there with one of our phase 1 UAVs. These are the waypoints that we selected, and this is the final trajectories. You can imagine that there is an error. Maybe the error here was up to 15 meters, that can be interesting in some cases. So for doing that, this also has impact in the case of using different UAVs, because you can control their motion, or you can plan their trajectories in order to avoid collision, of course, but if the trajectory is not as expected, that could cause a problem. So from this point of view, we developed a method in order to plan the trajectory of different UAVs in a statistical way in order to prevent the possibility of collision, or let's say not prevent, but reduce the possibility of collision in a statistical way. We are essentially using one method that is well known in robotics, which is called bounding box. Okay. And after that, we developed a method that in robotics is called rapidly exploring random tree. I don't know if some of you maybe have heard about that. Okay, it's an heuristical method that essentially builds a tree in order to, and it's very efficient. Okay, now this is a topic in which that is quite active in robotics. In the last ICRA, a number of papers have been proposed that are much faster than this. But essentially, what we're using an evolution of the basic RRT method. Okay, and also we need to evaluate the trajectories. Once that we have defined a trajectory, we have to evaluate that. And to evaluate that in a statistical way. So we perform Monte Carlo simulation. I don't know if any one of you have heard about that. Yes. Essentially, the idea is to put noise in a simulation and to see the result, to see the effect of noise, essentially. So we put a number of particles with different noise samples, and we measure the evolution of the trajectory considering the particles. Each of the particles consider different situations of wind. In the end, the method is capable to say with 90% of the conditions of winds, there will be no collision. Okay, this is exactly what we wanted to do. Okay, this is the implementation and integration. This is exactly what you asked before. This is a state machine in which everything is put in the system. So essentially, the basic steps are the following. You have a number of nodes that are deployed in an area. You know the area, okay? So the VCC, which is the visualizer, the user selects a certain area. It commands that to the control system. The control system in Planet, and the control system just commands the UAV to start each of the missions. For instance, new data collection mission. Okay, you have a number of nodes. So the first thing is that one, when you are sent an area, you have to check that that area is consistent. Okay? Once that you check that it's consistent, you calculate a thick-thumb pattern, okay, considering the number of UAVs that are available in order to survey the area. Once this is step. Okay. In the next step, once that has been computed, it is sent to each of the UAV. The UAV just fly there, and they send packets to the nodes on ground, commanding activate, activate, activate. Okay. So there is a node. Well, of course, I didn't say, sorry, but the UAVs have a node that is physically connected to a computer on the UAV. Okay. So you can in real time command the node to do things. So this is implemented in a computer, which is the control computer. Okay, it sends commands to the computer of the base station of the UAV. The computer of the base station on ground of the UAV sends commands to the computer on the UAV itself, and it commands to the node, and then the node sends the packet. Okay, it is like that. Okay. So in this case, when the nodes on ground receive the packet, just they activate, they start performing the network formation, they select their clusters, and they organize themselves into clusters. Okay? So in the next state here, this is just a wait state. Let's say that the UAV just repeats the fixed-up pattern, doing nothing, just letting time for the nodes to agree which is the best cluster head, etc., etc., etc. Okay, just to have a number of time. Then, in the following step, they have already identified the cluster head, so the UAV performs the same pattern, asking, please, those who are cluster head, tell me who you are. Tell me who you are. Then they have a list of the cluster heads, and in this step is again a wait lab in order to allow it converts and everything right. And in this step, you compute the path in order to collect the data passing through the collection zones only of the cluster heads, okay? And you give it to the UAV, and you command the node to establish the protocol for data collection. So the UAV says, I'm the UAV, please cluster head X, give me your data, and so on.
Just to make sure, so for the first step, you need to go through with all the nodes, installed nodes, just to know which one are the cluster hash.
Yes.
For the first
yes, because we are assuming that the nodes can be there for maybe months.
right.
So you have to activate the nodes and then deactivate the nodes after everything
It
finished.
won't be so bad to do that because it will be just once a month or something like that. So
Yeah. It can be once a month, or it can be as frequent as you want. So you need to activate and then deactivate in order to have to enlarge the lifetime of the batteries of the nodes. So first you activate, then you know who are the cluster heads, and then just you communicate just with the cluster heads. Okay, this is the. And when it finishes, you just send a packet deactivating it everything. So deactivate it, sleep. So
just maybe a stupid question or something, because you are asking everybody, are you the cluster head? Are you the cluster head? Wouldn't it be more practical just receive the information from each node? Maybe the packets are smaller, so more efficient.
we think if you send a packet, it's something like a confirmation. So I think it's more it's more efficient. So you can be the nodes are silent unless something asks. I don't know if I'm late or not. Yeah? I have to. Okay. This is one of the schemes of the implementation of the data collection. If you want some details, I can comment. But essentially, it implements what I said before. I wouldn't like to repeat unless you have some doubts. Okay. And also, of course, this is the implementation of the state machine in case that you have only one data collection. Imagine that you need only data each a month. So you just go, activate, get the data, and then deactivate everything, and then the UAV just lands it. Okay, this is this scheme. Okay, but of course it is possible. No, this is this scheme. This is this scheme. Okay, but imagine that you want, for instance, to take one data now and one data collection in 1 hour, another data collection, another data. So what you do is you perform the data, okay? You perform the data collection, you activate all the nodes, the UAV lands, but the nodes are activated. So the nodes keep on registering data, logging data, etc. Okay? So after an hour, the UAV takes off, and it doesn't have to activate everything. It only has to say, please give me your data, give me your data, and then it lands again. So it's quite flexible from this point of view. One video or one experiment that we did many years ago. Okay, Yes, I like to use it because the video of the Planet project, the UAV is 400 high, so it's impossible to see anything. You can see like an eagle. You cannot see anything. This case, this is one video that we performed data collection in some previous project, national project, okay, not Planet. And this is one experiment we got in the last Planet experiments. We are going to have an experiment in 2 weeks' time, but this is of the last. This is the trajectory that we have. These are the nodes that were deployed. In this case, we wanted to perform experiments of in order to assess communication between ground and air. Okay. So these points are locations of the UAV when it receives data from any of the nodes that are here. Okay. This is the UAV that we're using. It's about 4 or 5 meters wingspan. And we have one node here and one node here, 2 nodes. There are 2 pods, to put. Okay. These are the results at what time. These are the PRR, different altitudes. Okay. So this is the Euclidean distance on the ground. Okay. At different altitudes. This is considered as all altitudes. That means that the UAV could receive data at 200 meters from the projection of the UAV to the 200 meters, quite a lot. Okay. Of course, the PRR was very, very, very low. Okay. But this is the PRR for the range of for this range of distances, which is almost 90%, which is not bad. Okay. This is the PRR for this height. This is the PRR for this height. Of course, if you go higher and higher, this is broader because of the antenna. We also tested one with different antennas, and because in this case of the Teros V, they are standard microstrip antenna. They are Teros V, in fact. Okay, so they don't are on ground, and they note that this on the UAV it has a omni antenna, has a directional antenna. In fact, not in directional. No, I think it's an omni antenna. It's an omni antenna. It's a lambda antenna. Okay. Okay. So once I have the data, the final thing is that you need to get a sampling of the terrain in order to measure the pollution. Okay? So you have a number. This is a result also of our project in which 3 UAVs were collaborating to transport a load that couldn't be transported by any of these because the load is heavy, is much heavier than their payload. And in this case, this is the first time in the world such a thing was demonstrated. They are fully robotics and they are fully in coordination. And it is very difficult to control an helicopter. I don't know if you have tried to control an helicopter. It is really, really difficult. I'm speaking, of course, about real helicopters. I'm not speaking about real UAV helicopters. I'm not speaking about the toys that you can buy for your children, which are very easy. Okay? But in this case, this was the very first time that it was demonstrated. Okay? So the idea in Planet was something similar. Okay? So the idea in Planet was something similar. We wanted to deploy not a heavy load, but a robot like this. So this robot is capable of sampling. Well, we have still to have some adaptations in order to design the sampling device. Okay. Essentially, we want an helicopter to pick the ground robot, deploy at a certain location. Then the ground robot will move. You can teleoperate that. I will tell you later. The ground robot do what it has to do, and then he calls the UAV to pick it. Then the UAV just go and pick it back, and that's all. Okay. So in this case, we have to design the robots, and also we have to design the strategies in order for deployment and retrieval. Okay. So it has very compact design, lightweight. Okay, because it has to be lifted by the helicopter and it should be all terrain. Essentially, we implemented that with 2 controllers. With low controller, which is a PIC, okay, and is responsible for controlling the engines. And the high controller was on a smartphone, was a Samsung Galaxy 2 with dual core, a lot of sensors, gyros, GPS, cameras, etc., etc. Okay, and it was connected through a 5 GHz Wi-Fi with a helicopter. It has USB host in order to connect with the Telos base that is installed on the robot itself as well, with a protocol, with the additional protocol I mentioned before, and also it's connected with Bluetooth to the low-level control. Okay, so we're going to have integrated experiments of this thing also in 2 months' time. A lot of experiments in 2 months' time. Let's see. And of course, one important thing here is not only to deploy but to recover. Recover is very difficult because the GPS of the smartphone is not accurate enough to allow good recovery. So you have to design a device to grasp the ABB, to grasp the robot, and to recover it. So you have to accurately know the location. For doing that, it is necessary to have a minimum accuracy of 1 meter. Let's say that the helicopter can recover the robot if he knows the location has an error of less than 1 meter. Because it has the helicopter has a camera, okay? So if you know where it is more or less, it can recover it. But of course, you have to provide the localization with an error of 1 meter, which is not easy. How we deal with that? Using signal strength localization. We have a number of nodes in the environment, okay? These nodes know the location, okay? And then they communicate with the robot, okay? And the robot computes the localization using the signal strength. Okay. How we do that? We do that by, let's say, an innovative approach. There are many methods to compute localizations using signal strength, okay, but the accuracy is not lower than 1 meter, okay, but we developed a method that accuracy is 1 point something, and something means very low, okay. So the method is based on an estimation method that is called essentially the Kalman filter. I don't know if you have heard about that, I can imagine, okay. Kalman filter is an optimal estimator. We developed, let's say, a similar implementation to the Kalman filter that is called information filter, which has some properties or some advantages. And also we developed that with a module that is capable of saving energy. I will explain now here very briefly. Okay, this is the basic scheme of a recursive Bayesian filter, essentially the Kalman filter. You have 2 steps. You have the update and the prediction. The update, you put the measurements, the signals of the measurements, and with the measurements you estimate the state and you predict. Okay, this is a typical instance. Okay, but of course we are interested in doing something, let's say, a little bit more efficient, and we develop a method that is distributed. It means that in traditional schemes, the localization of the robot was computed by the robot itself. Okay? In this case, the localization of the robot is computed in a distributed way between the robot and the nodes. Part of the filter is implemented in the robot, and part of the filters, this part which is very efficient, okay, is implemented in the nodes themselves. So from this point of view, we use a very efficient way of implementation. And this method also has a scheme that for us is quite interesting, that is a method to let's say, activate and deactivate nodes in an efficient way. You would like to know, in general, if you have one node that is active, it spends energy, it's not suitable. So we develop a method that is capable of identifying which nodes provide information, not measurements. Information is another concept, okay? Information that are suitable, that is good for localization, and which nodes do not provide information that is suitable. They provide measurements, but the measurements are for nothing, are useless from the information point of view. So from this is just a simple scheme. Imagine that for instance, you have one node here that is already active, okay? This is the location of the object, and this is the uncertainty around the object that we have, okay? We model the uncertainty using Gaussian distribution. So this is the Gaussian distribution. I mean, this is a Gaussian distribution that is here. Okay. If the Gaussian distribution is very narrow, it means that you have very, very certain localization, and it's very spread, it's very high. The localization is very bad. The uncertainty is very high. So in this case, this node is activated, and with estimation, this is the estimation that it gets. Okay, this is the estimation of the localization that it gets. Now the question is, which of these nodes, nodes A or B, provides better information for localization? So the method essentially performs as follows. It launches an hypothesis. Let's see what happens if I activate A. In this case, if we activate 8, the localization would be like that, and the final estimation would be like that. The sum of Gaussians would be like that. The superposition of the Gaussian should be like that. And in case of the second hypothesis, this is here, this is the second Gaussian. The interchange, the superposition between them should be like this. So which is more accurate, this and this? This is more accurate. So the decision here is we don't need to have this sensor activated because it doesn't improve the estimation, but we need to have this sensor activated because it does improve a lot the estimation. So this is the main idea. Of course, this is formalized in a mathematical way using entropy. Okay. I have a number of papers regarding this if you're interested. I wouldn't like to go too much detail, but it can be implemented very, very efficiently. We implemented that in a standard TOSB, and it worked quite well. And we perform experiments here in the testbed. This is a photograph of our testbed. This is the estimation that we got of a moving object. In this case, the robot was the object that we wanted to follow. These are the sensors that we use. And in this case, this is the estimation that we obtained. This is very, very near the ground truth, which is almost overlapping. Okay, and this broad band is the actual time. Okay, and this is for one axis, and this is for the other axis. And this represents the times in which the different sensors were active or not. In this case, this sensor was active during the whole period, but this sensor, for instance, was almost inactivated, saving energy during the whole period. So this is good in order to save energy to make localization accuracy. The result here makes that the system deactivates the nodes that do not provide energy, so that do not provide information, so saving energy. As a result, the method can reduce up to 70% of the energy without affecting the estimation. Okay, I have some papers if you want to, if you're interested.
Excuse me, what is the estimation error here?
It's almost. It's
I don't see no
20 centimeters, something like that. It's nothing. Well, in this particular example, it's almost nothing. This part is almost nothing. Okay, but in this case, we tested that with cameras. Okay, not with in this figure. This is the figure that we found, but of course we have also some results with some publications, a number of publications in IROS. Do you know IROS, conference IROS? Regarding this, these have been well affected in IROS. Okay. So, just to conclude, I'm very sorry because I think it took a little bit longer than the planned time. Okay, almost. I think that UAVs, aerial systems, and also wireless systems are very powerful tools for environmental monitoring, but not only wireless systems. We are used to have another application of wireless systems for application monitoring, but there are a number of tasks that cannot be done using only wireless systems. And in this case, there are a number of complementarities that are of interest using unmanned systems. Okay. In this case, I just put a number of examples. We have developed more because this is our main research topic there. We have a number of projects, not only Blended, more projects regarding this topic. And in this case, we demonstrated this we are working on this in Blended and will be demonstrated in the next two weeks for cooperative surveillance using aerial systems and wireless sensor networks for deployment, for data collection, and also for pollution sampling. Of course, this is very interesting in real applications in which there are many things that are unpredictable, so you have to adapt in a dynamic way. The environment is very harsh and is very with very low accessibility. These are the environments in which these synergies can be exploited in a best way. And of course, here it is very important to have feedback from the real application of the field experience. It's absolutely important because there are many things that you can think that you have foreseen, but in the end you go to the field and something happens. Okay, so it's very important to have control experiments, but in a real cases. Okay, so this is the experiment we're going to perform in 2 weeks is in Doñana, which is in the middle of the field. It's about 1 hour to the next location, to the next village. There's nothing, electricity or nothing. You have to you have to bring all your equipment, meaning by electricity, network, absolutely everything. But this is the real case of a disaster is like this. Okay. So this is the end of my presentation.